Hello there and welcome to, yes, yet another flat earth debunking video. Now, in this video, what I want to do is have a look at one of what flat earthers seem to think is a core argument in their quest to prove that the earth is flat. And it basically, I'm sure you've heard it, it goes something like this: water always finds a level, water's always flat. There's no level on a sphere, or water can't curve on a sphere, or if you pour water on a ball, it just falls off. I mean, various versions of this thing that because water is flat, that the earth must be flat. Now, the first thing to say is it doesn't even stand up as an argument, because all they're doing is observing that water is at least approximately flat on a small scale. And there's absolutely no justification for leaping to the conclusion that it must be flat on a large scale. There's none. There's no intellectual justification for that claim at all. And what I'm going to do in this video is go through quite a few ideas to do with forces in water, and talk about how it is that water comes to have a flat surface and how it is that water can curve. I'll be going over some things that I actually talked about in some videos I did about 7 months ago. So there'll be a little bit of repetition with those videos, but I'll be taking it in a different direction. Now, in those videos, I talked about buoyancy and gravity, and I also talked about pressure and force. And one thing I did in those videos was I fudged over a little bit the difference between pressure and force, because I didn't really feel it was necessary for that video to go into that. But I want to be a bit more clearer in this video and talk about what pressure is and what force is, and then go on to talk about how that helps us to understand the way that water behaves on the surface of the earth. And also, I'll talk a little bit about why density alone doesn't explain anything. Right, so the first thing we'll talk about is pressure and force and what the difference is between them. So suppose we've got a container. Like this. Not well drawn, never mind. So this is a box, and within the box there's a fluid. Now, a fluid could be a gas, it could be a liquid. Now, what you've got in a fluid is a substance where the atoms or the molecules are free to move around. They're not bound to each other. So they're free to move around on their own through the substance. And a gas or a liquid, a fluid, will exert a pressure on its surroundings. It's constantly pushing out against whatever's pushing against it. So if we've got a fluid inside this box, and we'll assume that there are no other forces acting, there's no gravity, there's nothing else, there's just a fluid inside this box, it's pushing against all the surfaces. All 6 surfaces, it's pushing out against them. Now, we call this tendency for the gas to push out, or the fluid to push out, pressure. So the gas has something we call pressure, and that's pushing against all 6 surfaces. So we consider that surface on the bottom. I'll draw it again here. Okay. The fluid is exerting a pressure P onto this, which means it's pushing onto the surface with a force, which equals F. So what do we mean by, what's the difference between the pressure and the force? Well, you can think of the pressure as like a property of the fluid. It's something that's contained within the fluid. It's a property of the fluid. It's pushing out with a pressure. The force is how much it's pushing on that particular surface. So it's related to the area of the surface. So we'll call it area A. So the pressures inside the gas pushing out on all the surfaces, the amount that's pushing on any one surface is the force it's pushing on that surface, which is related to the area. So basically, the bigger the surface, the more force that pressure is exerting on it. Which leads us to, we can express this in two different ways. We could say that the pressure is the force over the area, and we can say that, or we could rearrange that and say the force equals the pressure times the area. Okay. Now in mathematics, we don't usually put times, we just usually write PA. That just means pressure times area. Now I will say, in this video, I'm going to be using some mathematics and algebra like this, and I know that puts some people off, but I would ask you to stick with it because I will try and give you simple physical concepts that you can visualize to help you think about what this mathematics is telling you. So don't be put off by the maths, because I'll give you physical ideas to think about that you can visualize, like I said. So this is the first thing, it's pressure and force and what the difference is between them. Next thing I want to talk about is density and mass. So suppose I've got an object, like a cube, like this. So it's not very well drawn, and it's got a volume V, and it's got a mass M. Now the density is just defined as how much mass there is per unit volume. So the density, now it's given the Greek letter rho, and it's defined as the mass divided by the volume. And again, if you want to, you could write that another way. You could say that the mass is the density times the volume, or mass equals rho v. Okay? So mass is the amount of matter there is in the whole thing. Density is how much matter there is in 1 unit per unit of volume. Okay? Just one mathematical thing I want to talk about, which is something called the volume of a prism, because I'll be using this idea. Now, prism in mathematics is basically any solid object that's got what we call a cross-sectional area. Now what that means is that if I cut this object somewhere along its length, that shape will be exactly the same shape as the shape that's at the end of it and at the bottom of it. Okay, we call it the cross-sectional area. So if we call that area A, the cross-sectional area A, and now this length here, if it's lying down you could call it length, if it's standing up we usually call it height. Now I'm going to call it depth because that's going to relate to what we're talking about later. So we'll call it that the depth of the prism. And the volume is very simple. It's just the area times the depth. Right? So if you know what the cross-sectional area is and you know the depth, you just multiply them together and that'll give you the area of that prism. Right, so we've covered pressure and force, covered density and mass, covered volume of a prism. Right, so next thing I want to talk about is just something very crucial to understanding what's going on here. And it's something flat earthers just tell an awful lot of lies about. They claim that there's no such thing as gravity. Well, whatever you want to call it, there's a force. Okay? Now I talked about this in the other video. There's a device that you can use called a Newton balance. You can hang objects on it. And all it is like a spring. It's like a calibrated spring. And there'll be a little indicator that'll pull down. So supposing we're hanging on this Newton balance, a container with some water in it. like this. Now say it's 1 litre of water. Now 1 litre of water is approximately, has a mass of approximately 1 kilogram. And this will pull down with a force of 1 g newtons. Okay. Now we multiply the mass by g because it comes from Newton's second law of motion, which is force equals mass times acceleration. Now we know if we drop something on the earth in a vacuum, it starts to accelerate with g. So there must be a force acting on it, which is the mass times g, which is acceleration. So to get the force is just going to be the mass times g. And we measure it in newtons. Now this is what we call weight. In everyday language, when we talk about weight, we usually mean, what we really mean is mass. Because we might say that we weigh so many kilograms or so many pounds. What we really mean to say is that's what our mass is. Now, when you weigh yourself, what you're doing is you're using your weight to measure your mass. Now, the fact that this water can pull this Newton balance spring down means that there's a force. Okay? You can only stretch a spring with a force. It's not possible any other way. This means that there is a force. It's not theoretical. It's not just a theory, as they like to say. This is the way the world is. There's a force pulling things towards the ground. Now, if we do the same thing, what we have twice as much water, say 2 litres, there'll be a force 2F pulling down. This will weigh 2 kilograms, and the Newton balance will measure 2g newtons. Okay. Now, this is absolutely crucial, and it's really important to understand the 2 points being made here. The first is that things with mass have weight, which is a force. It's a force that's pulling them down towards the ground. It's measurable because it can stretch a spring. If you double the amount that there is, double the mass, you double the force. So there's a force pulling things towards the ground that is directly proportional to the mass of the object. The density of the substance doesn't matter. It's got nothing to do with density. It's only to do with the amount of mass, and it's a force. Okay? You can't get away from that. It's there, it's real, and you need it to understand the way that water behaves. So let's think about water in a container. Now we know that water fills the container up like this. Now in the air there's a pressure that's pushing down on the surface of the water. Now let's think about a horizontal line somewhere down here in the water. And this line is at a depth d. Now pushing down on this line, there'll be the pressure from the air pressure pushing on the top of the water, plus the weight of the water, because the water has weight. There's a force. So this water is pushing down on that line. So say that water's got mass m. We'll write it in here. Mass equals m. Then the force that the water's pushing down with is mg. Okay. Now, the mass of the water we can say is the density of water times the volume of the water that's in here. Okay, so we can say that this water here has got volume V. So density times volume, like I mentioned earlier, gives you the mass. So that's rho Vg. Now the volume of this, now this shape here is a prism, so this surface here is A. See, we call this surface here, and this, so this surface here will have an area of A. So this equals rho area times depth. So the area of this surface here times the depth gives you the volume of what's in there, G. So the force that the liquid is pushing down on here is equal to the density of water times the area of the surface times the depth of the water times G. But we want it as pressure, so the pressure will equal all of that divided by the area. Because remember, pressure, let's go back to the beginning. Pressure is force divided by area. So it's rho A dg divided by A. Now the A's cancel, so the pressure is just rho dg. Okay. Now if you don't follow that, don't worry. The main thing is to understand this, right? That the pressure exerted on this surface due to the water, the weight of the water, is the density of the water times the depth of the water times G. So the total pressure acting on this surface is air pressure plus rho dg. And the water isn't flowing around. Well, there's no net movement in the water, so all the forces must be balanced. So the water must be pushing up with a pressure here, the pressure of the water at that depth, so we just call it PW for water pressure. So these two forces must be balanced. So the force pushing down is the pressure pushing down, sorry, is the air pressure plus the pressure due to the mass of the water, which is density of water times depth times G, and that would be balanced by the pressure in the water pushing back up there. Now, without extra forces, the pressure in a fluid will evenly distribute itself. Now, if I go back to here, I started with a fluid inside a box with no extra forces. Okay. Now, you can think of this kind of as like a spring that's pushed between two surfaces. So this is just in one dimension, this is three-dimensional. So the spring's pushing out on both surfaces and there'll be forces pushing here. Now we could say that the spring has a tension. Now without any forces acting along the length of the spring, the tension will evenly distribute itself along the spring. If you put your finger here and bunch the spring up at one end, so you get this. So you're pulling it this way, then you get more tension at this end and less in this bit. But you can only have this uneven distribution of tension if there's an extra force acting along the length of the spring. You take away that force and it evenly distributes itself along the spring again. Well, it's a similar thing with a fluid in a container. If there's no extra forces, you can't have a build-up of pressure in any area. Say you did get a build-up of pressure in one place, then all that would happen is the fluid just flows away from that area. So the fluid will flow from places of high pressure to low pressure, and then the pressure will just evenly distribute itself through the fluid. So without any extra forces, you can't have any kind of uneven distribution of pressure. Now notice here, in this situation, the pressure acting on this surface here is determined by this here, pressure of the air plus the density of water times the depth of the water times G. Now the only thing that is variable in this is the depth of the water. The pressure, the density and G are all constant. So the only thing that varies in this is the depth. So the only thing that determines the pressure at this level is the depth of the water. And that's really important, that's crucial to understand. And you cannot explain that with density alone. You would not have this thing, we call this a pressure gradient, which means that the pressure increases as you go deeper. You cannot have that with density alone. That doesn't explain it in any way at all. Density cannot explain this. Because water is a fluid, which means, like I said, all the molecules are free to move around all the time. So the density would be evenly distributed throughout the liquid, or the fluid, or whatever it is, without an extra force. So you can only have a pressure gradient because there's a force acting, and it's the force that is proportional to the mass of the water, which means the deeper you go, the more pressure there is. Now notice as well that there's no forces acting horizontally. The force is acting vertically. So this means along this horizontal line, there can be no pressure gradient. So the pressure must be constant along this horizontal line, because there are no forces acting along that line, like on the spring to make it bunched up at one end. So this must be like the spring when there are no forces acting on it, so the pressure must be the same all the way along this line. That's crucial, and I'll explain why in this section here. Let's consider a situation like this. You've got a container. It's got a divider, but the water can flow at the bottom here. Now suppose the water is at two different levels. So that's depth 1 and that's depth 2. And you've got air pressure. So the pressure acting on this bit is air pressure plus rho d1g. The pressure acting on this bit is air pressure plus rho d2g. And notice that d2 is bigger than d1, so the pressure on here, the pressure on this section must be bigger than the pressure on this section, which means it's like the coil, it's like the spring bunched up at one end. But there's no forces acting to keep it like that. So what happens? Well, the fluid will just flow in that direction because this pressure is higher than this pressure. So the water will flow. And then what you'll end up with is this. So the both levels would each, say we call it depth D. So the pressure acting on both sides now is just air pressure plus rho dg. Air pressure plus rho dg. Okay? So both sides must have the same depth. So you've got the same pressure here, which means the surface of the water must be flat. Okay? You can only, the reason water has this level flat surface is because there is a force creating a pressure gradient vertically, but there's no force horizontally. So the surface of the water must be at right angles to the force pushing down on the surface of the water. Because you can't have a pressure gradient horizontally at any depth. Any horizontal line must all be at the same depth. And that means that the surface of the water must be at the same level. And that's why you get a horizontal flat surface on water. Now density, in this density idea, there's nothing to prevent water staying in an uneven situation like this. Because according to this density idea, dense things just somehow magically move to the same level as each other, but the density is not determined by anything above it. So the density or the pressure, now, let me explain a little bit about this, because water, the density in water doesn't change significantly. It does increase very, very slightly. A tiny, tiny increase in density is a massive increase in pressure. But they say that the density increases by 5% at the bottom of the ocean. So say this is a depth of about 7 miles, then you will be getting a density increase in water as you go down. But according to the density theory, the density would have nothing to do with the weight of the liquid above it, because there's no force in this theory. So there can be no such thing as weight, which means there's no density gradient. But even if there was a density gradient in water, which you couldn't have that without the force, but you say there was, then it would have nothing to do with the depth of the water. So the water could have an uneven surface. So the top of the water could be any shape you want. So this thing that flat earthers keep talking about, oh, water always finds a level, water's always flat. Yeah, because there's a force acting, and the surface of the water must be necessarily at right angles to the direction of the force. And that's why the surface of water is horizontal and flat, at least locally. And density doesn't explain any of this at all, none of it. Now, just quickly, I'll recap on buoyancy as well, and why things float in, light things float and dense things sink. Okay. Now, I've touched on this in another video. So let's say you've got two lines in a water, right, and an object there. Right? And this is at depth D1 and this is at depth D2. There's a force pushing down on the top of the object. Okay, say we call it force 1. And there's a force pushing up the way, force 2. Now the force pushing down will be determined by the pressure at this depth D1. So we'd say we've got pressure 1. So it'll be determined by whatever the pressure is along this horizontal line in the water. The force pushing up will be determined by the pressure of the water at this depth. Now because you've got a pressure gradient, force 2 is very slightly bigger than force 1. Now, if this object has the same density as water, then it has just enough weight to make up for the difference between F1 and F2. So F1 plus the weight of the object will equal F2. And the thing will just sit in water. And that's why fish can swim, because they're basically the same density as water. If this thing is less dense than water, then it doesn't have enough weight to make up for the difference between this force and this force. This force wins and the thing pushes up. If this thing is more dense than water, then it has enough weight to win and overcome the upward force, and it starts to move down. Now again, you can only have this thing where density becomes an issue because you've got this downward force called weight. We call it gravity, which creates this pressure gradient, which means the pressure increases as you go further, which means the force pushing up is slightly more than the force pushing down. So whether it moves up or down depends on whether the weight of this object is enough to balance these forces, or if it's not enough to balance them, it'll either move up or if it's more than enough, it'll push down. And just another point about this as well, because I've heard so many flat earthers where they talk about this, where they'll talk about things floating in water, or air bubbles rising in water, or helium balloons rising in the air. Now this argument applies to helium balloons. It's the exact same argument. It applies to any fluid, whether it's a gas or a liquid. So whether it's an object floating in water, or whether it's a helium balloon in the air, it's the same argument. Now they seem to think that just because they've noticed that light things float, that that's enough to debunk gravity. Now, to me that shows that these are people who have absolutely no idea about the world that they live in. They don't understand the world. I mean, they have no idea what physicists are, what they do, what kind of people they are. I mean, the idea that all you have to do is point out the fact that a helium balloon rises is enough to debunk gravity, and that no physicist in 300 years ever pointed that out, is just childish. If you actually think that that would be enough to debunk gravity and gravitational theory, you're a child. You're a child in an adult's body. You're an infant. It really is pathetic. It means you've got no idea of the kind of people who make the world that you live in work. You're like a kid living with your parents who doesn't understand where the money comes from that puts the food on the table. You really are just a child if you think something like that. It's pathetic. Anyway, I know this video is a bit long, but there's one thing I want to go on to, which is explaining how it is that water can then curve or cling to a sphere. Now, the force that I've been talking about, this gravitational force, or we call it weight as well, I've assumed that it's uniform, which means that it doesn't change with height and it doesn't change its direction. So its strength and its direction stay the same. Well, that's not entirely true. The higher you go, it starts to drop very, very small amounts. I mean, even at 5 miles, it's hardly dropped anything at all. And its direction is not uniform either. It starts to change very slightly over the surface of the Earth, very, very slightly. So let's play about with this force and change its direction and do something that's called a thought experiment. Now, a thought experiment is where you consider a situation that is not realistic to actually happen, but which we can actually mathematically conceive of. And the point of it is to try and help us understand real situations. So supposing you had a very peculiar situation where you have a line like this, and the gravitational force is acting in 2 different directions. Suppose on this side of the line it's acting in this direction, and on this side it's acting on this direction. Well, the surface of any liquid would have to be at right angles to the force, as we know, because you can't have a pressure gradient with that's at right angles to the force. So the water would have to do something like this. So the water would form this very peculiar shape like this, where the surface of the water was always at right angles to the force that's pushing down. Okay, so there's a force pushing down here in this direction, and it's at right angles to the water. And the same on this side. So the water would form this very peculiar shape. Now, in reality, this is completely not physically feasible, but it's mathematically feasible with our description of these forces. If you could set this physical situation up, this is how water would behave under this very peculiar situation. Now, let's consider lines through the water that have equal pressure, where they're basically going to form a line like this. So they'll basically be lines that are at right angles to the lines of the force. And I've not drawn it very well, I don't think. Okay. So if we consider, say, like a column of water from here to here, the depth, the pressure at the bottom of this column would have to be equal to the pressure at the bottom of this column, which means the depth of this column would have to be the same as the depth of this column. Okay, so the water would have to form this kind of shape here if you had the forces acting like this. All right. Now that's just to help us to understand that what the water does is determined by the direction of the force that's acting on it. So let's consider another slightly peculiar situation. Suppose you've got a square shape like this, and the force acting on the water is pushing in these directions. Then what would happen is the water would just wrap around the square or the cube like this. So this surface would have to be at right angles to the force pushing that way. This surface would be at the right angles to this force, same with this one, and this surface would be at right angles to this force. So the water would be pushed onto this, clinging to around, say it was a cube like this. Okay, so whatever, you can play around with the forces and you can get the water to do different things. Obviously, this is just mathematical. It's kind of like, say, a thought experiment. But in reality, what the force does is its direction changes very gradually. So the surface of the water will follow it like this. So any local area, the local surface of the water will be at right angles to the local direction of the force. But on a larger scale, we can see that the water will have to curve because the force is changing direction very gradually. So if you had a sphere, it's not very well drawn, but it must be a sphere, and you had the force was pushing towards the centre of the sphere all the way around, then the water would have to just follow right round like this. Well, it's supposed to be a circle, but you get the idea. And anywhere, the local surface would be at right angles to the direction of the force. And this is how water can curve, and this is how water can stick to a ball. But the ball has to be huge to have enough gravitational force to do this. Only something as big as the Earth could do that. Now, another thing that they keep saying is, well, if it's spinning, no, it would be spinning, the water would fly. The Earth is rotating once a day. It's hardly rotating, it's a painfully slow rotation. The amount, and I've done this in other videos, the amount that the rotation of the Earth would affect this is negligible because it's so slow. So that's not even really a factor in this. We don't even have to worry about this for this video. So this is why water curves, though. Okay, it's not really following the curvature of the Earth as such. What it's doing is it's following the change in direction of the gravitational force, or it's following the contours of the gravitational field. That's what it's really following. It's indirectly following the curvature of the Earth, because the curvature of the Earth determines the way that the gravitational force works. But it's the actual force that's making the water curve. So it's really following the curvature of the gravitational field. Another thing just to mention briefly before I finish is this thing about density again. Supposedly, in this theory of density, all of this could be, everything that we attribute to gravity can be understood in terms of density. Denser things move down. So if something dense, things move down and light things move up, apparently, just according to some natural physics of the world that they never explain. Well, one thing to say about this is, no flat earther can ever explain what is special about the downward direction in this density theory. They can't. Now, since they can't actually explain why dense things move down, they've got no intellectual defence against arguing that the direction that dense things move in could change. I could just as easily say, well, I've got a density theory that denser things always move towards the centre of a sphere. I mean, if this density thing could explain the things that we explain with gravity, which it can't anyway, but even if it could, there's no reason why you couldn't apply it to a sphere anyway. I mean, there's no objection they could make to that, unless they can give you a proper, rigorous scientific explanation of why dense things move down in this theory. They can't object to you claiming that the direction they move in could change, and in fact could always be pushing towards the centre of a sphere. They've no defence against that argument at all. So their density theory can be applied to the spherical Earth anyway, even if it was a proper theory, which it isn't. It doesn't even explain anything, but if it did, it could be applied to a sphere anyway, and they've got nothing to say against it. So I think that's about as much as I want to say. That's a bit longer than I would usually go on about. So I've just basically gone through why water is flat, locally flat, and how it curves, and how buoyancy works, how all of it can only be understood in terms of being a force. And this is the crucial thing here, is this. What I'm representing in this diagram here, which is you could physically do for yourself. There's a force pulling things down because it stretches a spring. Weight stretches a spring, and the amount that it stretches it is proportional to the mass. Not density, not anything else, just how much there is of something.